Ladies and gentlemen, the Institute for Mathematical Sciences, or in short IMS, is a university-level research institute at NUS. Its mission is to promote interest and research in the mathematical sciences and their applications. It organizes thematic programs and brings together foreign and local mathematicians and scientists for interaction, cross-fertilization of ideas, and collaboration in research. It also organizes public lectures to help instill and foster mathematical awareness and interest, and school lectures and math camps to stimulate students in the study of mathematics and inspire them to pursue a career in the mathematical sciences. This evening's public lecture is organized by the Institute in conjunction with the NUS Department of Statistics and Applied Probability and the Singapore Mathematical Society. We are pleased to have Professor Bryan Grenfell of the Pennsylvania State University as speaker. Professor Bryan Grenfell is a population biologist, focusing in particular on the dynamics of infectious diseases in space and time. He combines development of theory with pioneering analysis of empirical data sets from a range of diseases, from measles to foot and mouth disease and influenza. Originally trained as a zoologist, Professor Grenfell has worked on the dynamics of epidemics since 1980. He recently moved from the University of Cambridge, UK, to the Center for Infectious Disease Dynamics in Pennsylvania State University, USA, where he holds the chair of alumni professorship in biology. He has served on the UK government Chief Scientific Advisors Science Group that advised the UK government on the control of the 2001 foot and mouth disease epidemic. He is currently chair of the steering committee of the Models of Infectious Disease Agent Study at the National Institute of Health, USA, and a senior visiting scientist at Fogarty International Center, also of the National Institute of Health. Professor Grenfell was awarded the Scientific Medal of the Zoology Society of London in 1998, the Order of the British Empire in 2002, and was elected Fellow of the Royal Society of London in 2004. It is now my great pleasure to invite Professor Grenfell to deliver his lecture on the Epidemic Clockwork, Exploring the Population Dynamics of Infectious Diseases. Bryan.
Great pleasure to be here. So in this lecture, I want to give a talk that blends. I see several of my colleagues here, so they're going to criticise the generalities that I give in a public lecture. And they're going to have to put up with that, I'm afraid. I'm going to talk about really what is an epidemic and what makes epidemics possible to control, but also in many ways difficult to control. And this has great applied import at the moment, but this epidemic clockwork is also a fundamentally interesting piece of population biology in terms of our general understanding about how population works. And it's one of the most dangerous things about epidemics is that diseases can evolve. But again, as a picture of how evolution works, it's kind of interesting in that way as well. So there's basic science, but there are also these very big applications. This is really going to be an illustrated talk. There's one little bit of, it's not mathematics, it's kind of accountancy really, I want to go into, just to show what an epidemic is and what we mean by immunity at the population level. And anyone who's going to face an epidemic, it's really useful to have that machinery, I think. So there's a huge impact of disease on history. Here's a famous bulletin from the 1660s, 60s in London. It's a wonderful thing, this. It's got everything from causes of death to regulations about the contents of wheat and loaves. So it's all like it's here really. Many interesting causes of death. We won't go into many of the details. I think my favourite one is two people died suddenly there. Teeth, etc. We really don't want to know how things were in those days. But the big one was, if you look at the size of these numbers, 4,237 people died of plague. So this was the Great Plague with the summer flus, etc. The plague that Newton fled and then developed all the science that he did. Huge event in history. Subsequent to this, the development of vaccines and of antibiotics prompted the US Surgeon General, after the wonderful eradication by the World Health Organization of smallpox, to say that infectious diseases as a threat were completely dead. Now, we all know that that was a really, really dangerous approach, because that's absolutely not true. SARS, HIV, influenza, animal diseases like foot and mouth disease. We all know drug resistance and antibiotic resistance of bacteria in hospitals. We all know that there are huge current and future threats. Now, the war against pathogens is particularly hard because of two things. First of all, logistics. Often things happen very quickly, and we have to be prepared, and we have to do the right thing in a very timely and exact manner to get things right. And I'll talk about that in the context of the foot and mouth epidemic in the UK. And that's a particular problem in developed countries. So Niger is in the news a lot at the moment. Measles is a major killer of small children in Niamey. And if there's great poverty, then it's very difficult to achieve uptake of vaccines and so on. So logistics are very important for these new infections and for things in developed countries, but much more of a problem in developing countries. And then the other key thing that I'd pick out, I think, is that viruses, bacteria, worms, etc. evolve, often in a shockingly fast way, and that they can evolve, they're built to evolve around the natural defences of the host. But they're also fantastically good at evolving around the defences, the barriers that we put in. So that's something that I'm going to return to. So in this lecture, I'm going to talk about the diversity of impact of pathogens. I'm going to touch on that. I'm going to use measles, which is really the simplest example of this, to explore the anatomy of a viral disease epidemic. What do we mean by an epidemic? By the increase in declining cases. How does vaccination operate at this population level? And the concept, and I'm going to call this population immunity. Immunity from vaccination or from natural infection at the population level. There's a linked idea of a more technical one of herd immunity for the specialist, but I'm just going to talk about this in my lecture. So let's think about the diversity of parasites. Just to say that I'm also then going to come to logistics and talk about that in lessons from the control of the foot and mouth disease epidemic. And then I'm going to illustrate the evolutionary question just with some general illustrative points about influenza. So we're not just talking about viruses here, though. There's a huge diversity of parasites, and thanks to my colleague Peter Hudson for this slightly busy PowerPoint slide. There's a huge diversity of parasites from tiny packages of nucleic acid viruses up to large worm parasites. The sperm whale is, I think, the largest nematode parasite, which is many meters long and about an inch, about 3 centimeters thick. So parasites can be very large as well, and they exert a huge toll. Now, we think about parasitic threats often in terms of pandemic threats like the 1918 influenza. Here's a ward in trenches at that time at the end of the Second World War. But endemic diseases are also extremely important: tuberculosis, malaria, HIV/AIDS, and many of these, measles is a recent success story, but many of these are as dangerous as they ever were or on the increase. So a huge threat to parasitism. So what I want to do is illustrate the basic anatomy of an epidemic, talking about measles, and this is the bunch of people who were involved, and in particular Dr. Junchuan Xia, who used to be in Cambridge and is now here, has been very important in a lot of these recent developments. So let's think about the epidemic clockwork, this population herd immunity thing, and vaccination. Well, let's look at the natural history of measles first. So, as I say, it's an RNA virus. It's a virus code with its evolutionary genetic message coded by RNA, and we can summarize the natural history in this very simple way. By the British author Jerome K. Jerome, love is like the measles, everybody gets it. So if I add slightly less felicitously, they get better and they don't get it again, then that is essentially the mathematical problem. That's essentially 90% of the No other disease is that simple, but that's essentially what happens. So let's clothe that a little bit. So after a short period, as a small child, when if your mum had the infection, you get the antibodies and you get passive immunity, children become susceptible. They're then breathed on into respiratory infection by infectious people. And then they recover, assuming this isn't a deadly infection. It can be deadly, particularly for infants in developed countries, and when it's invaded islands, for example, where the infection's not seen before, it's killed large proportions of populations, so it can be very deadly. But unusually here, unlike as we'll see later on, influenza, for example, recovered individuals, if you do recover, seem to be protected for life from subsequent infection. Our immune system's very effective against measles when it's primed by a previous infection. So that you really do move in this direction. And you can do that in two ways. One is by being having natural infection, and I and our chair today are old enough to have had a natural infection, and many other people in the audience will have been given artificially a vaccine, very effective vaccine, which is, in this case, an attenuated, a weakened form of the virus, which effectively moves you into this recovered class as well. So it's that simple progression, that simple natural history. And here are the dynamics, the pattern of epidemics. So here's an epidemic, a sharp rise in cases, and then often a decline. It doesn't have to be a decline for some infections, but for these very short duration infections, you get measles for about 10 days normally. You get an increase and a decline. And there are a series of violent epidemics in that way. Just to show, these are data for England and Wales for the last 50 years, just to show this a little bit more dynamically. So the number of cases here for just 60 of the cities is donated by the sizes of the circles, and then London in yellow and the rest of England and Wales are shown in these series at the top. And I'm just going to whiz this through just to illustrate to you how dynamic a process it is. So you see these waves of infection moving through, and there are lots of kinks in how this happens and how schooling is important in this childhood disease and so on. But you see dramatic epidemics. You see the rise and the fall of the epidemic, and then and you see evidence for waves and so on, and all sorts of other lovely complexities. So the spatial spread of infection, most famously, I suppose, of the Black Death, is extremely important. And you see that in the vaccination era, then they really got their act together, and measles became at a lower and lower level, and it's now at an extremely low level in the UK, the US, Singapore, many countries that can achieve high levels of vaccination. So how does that flow of love is like measles, everybody gets it, everybody got it as a child effectively before vaccination, you don't get it again, you're only infected for a short period. How does that affect the pattern of the epidemic? Well, what happens when you get an epidemic? So after maternal immunity, you move into the susceptible class, you're then infected by these people, and then you move through to the recovered class. And let's assume that we start an epidemic when there are lots of these susceptible people, and then we watch how it spreads. And the key number here is called the basic reproduction ratio of infection, and it's the number of secondary cases if everyone is susceptible. So if we imagine, I'm sure she's completely uninfected, but if we imagine Professor Isham there wandering around at random in this population of people, breathing on them, and let's say that R naught was 2, then on average she would infect 2 people. Now, they also then would infect 2 people, and they also would infect 2 people, and therefore the epidemic's going to tend to increase. And therefore, knowing what this number is really summarizes a lot about the characteristics of the infection. Now, in the few days that you're infectious for flu, for example, even for flu in a pandemic when everyone would really be susceptible to a new sort of flu, and I'll come back to that later, then that number would be about 2 grams. For SARS, it was kind of that range as well. Not too large, but certainly big enough to make it increase. For measles, it was probably about 10 times that size. probably. So it's extremely infectious measles, and that's why you've got these very violent epidemics. So let's just try and illustrate this idea of this kind of geometric spread of the epidemic with a little cartoon. And I also make obeisance to Carlos Castillo Chavez, who also has a similar movie to this. So you can be susceptible, and let's kick off with everybody susceptible. I can't remember why I made this person sad there. This is the basic heterogeneity of populations, I suppose. You're susceptible, and then you get infected, and then you get recovered. And let's seed the infection with an infected person there. And let's say R naught was around 5. Well, this infected person is going to infect, let's say, around 5 people, and then they're going to recover. They're going to move to the recovered class. And then each of these infected people, and let's imagine they're moving around somewhat, they're going to infect around about another 5. So the infection's rapidly going to spread, you see. 5 is a big number in that way, but even 2 over a few generations, and each click of the mouse here is really a generation of infection. Infection's going to spread very quickly. But in this tiny population I've got here, you see that there's effectively the rate of spread is going to be self-limiting. Because if this was the total size of the little population we've got here, let's say it's a little village, then these people can't infect each other because they're all going to recover, and they can't infect these recovered people, so they can only infect the blue ones, and there are about as many blue ones as there are red ones there. So if the effective value of that reproduction ratio is going to decline, it's self-limiting because you run out of susceptibles effectively. So let's go back to this. So what happens then, as the epidemic spreads, it's going to use up the fuel effectively that keeps it going. Each case is going to produce less and less secondary cases. So now, if I'm wandering around and R naught is 2, and half of you have seen the infection before, then I can only infect half of you. So therefore the infection is going to turn over. So let's just, and this is the bit of accountancy, let's just close that for a second and imagine what happens when the epidemic dies down. And we can make a very powerful calculation, which is a calculation that's been made in many contexts over much of the last century by epidemiologists in many ways, but it's actually incredibly robust in many ways. So the initial epidemic depletes this pool of susceptibles, and therefore the effective value of this R naught thing, which only really applies when everybody's susceptible, is reduced. Now, just as I said, and this is just complete common sense, that this effective value drops in line with the proportion of susceptible. So if I could infect 2 and half of you are removed or immune, then I can only infect half of you, that's 1. So, for example, R drops in line with the proportion of susceptibles. So if R naught was 10 and the proportion of susceptibles was a half, then you can only infect 5 maximally. So what we would like if we were trying to control the infection is if this effective value is less than 1. So if I infect on average half a person, so sometimes I infect 1 person, sometimes I don't infect anybody, on average I infect half a person, they infect half a person, and so on, the infection is going to die away. So if we could get the system to the point when that was always true, then this disease cannot invade. And that's really what we're trying to do. Now, you see that this allows a lovely calculation. You can do this mathematically, but this little picture just summarizes it. Because if we can keep the number of susceptibles below that level, because this thing's turning over because the susceptibles are declining, and where the epidemic turns over is where R is less than 1, and that's where the susceptibles have declined to that level. If we can keep the susceptibles below that level by vaccinating, or if this was an animal population, chickens and flu and so on, if we had to by culling and so on, if we can keep them down below that level, infection can never invade. And an interesting thing here is we don't have to get everybody. We just have to get enough people so that the sums work such that each case causes less than 1 case. And this is this idea of population immunity, or the linked idea of herd immunity. And at critical levels, but it's therefore very important. So that's the bit of technicality in the talk, but it's a basic calculation. When you're trying to control disease, that's what you're trying to do one way or another. You can also do it by reducing people's contacts, by quarantine, and of course That was the only recourse we had in some cases, if there aren't vaccines or drugs, for example. So the infection can therefore never invade the population. That's what all control measures are trying to do. And just one more graph then, that critical proportion vaccinated, it's quite easy to show that the bigger R naught, and again it's just one more twist of the accountancy to show that, or of the mathematics, but it's a common sense thing. The bigger the R naught value, the harder you've got to try to reduce that down to an effective value less than 1. So that was about 80% for smallpox, and it was one of the reasons that smallpox, not very transmissible, was able to be eradicated. There were lots of other reasons, but that was one of them. For measles, it's over 95%, for example. For SARS, it would have been further down. For flu, it would be down more like here. If you could immunise half the population against all sorts of flus, then you'd be well on the way to it not being able to invade populations according to those calculations. So this is a classic picture, and again, it just really comes out of, illustrates lots of ideas, and it comes out of the application of mathematics, and just really a graphical application here to understand how epidemics work, how this propagation works. So let's jump straight away and apply that. Think about logistics. And think about the link between epidemic dynamics, control, and logistics in a real spatial landscape. So this is much more complicated. This isn't a population where I'm assuming that someone's wandering around and infecting people at random. It's more complicated than that. And the recent example I want to take is this, an animal disease, very, very infectious at the individual animal level, foot and mouth disease. And this is work really mainly by Matt Keeling, who's now at Warwick University, and we had a bunch of other great collaborators here from Edinburgh and from Oxford. We were one of the groups who were modelling the 2001 GB epidemic and thinking about future policies. So in summary, I want to talk about that and try and bring out some ideas about logistics. So how did it start? This was a farm in the northeast of England, a pig farm, and it's probable that infected imported meat was fed to the pigs, and the pigs then spread the infection to sheep. And it wasn't spotted for quite a long time, probably for several weeks. And because of economics, actually, because of the quota system that the EC uses, certainly used to use for compensating upland farmers and so on, you had to have a certain number of sheep. So people would sell sheep at a great rate and move them around. So if you wanted to design a strategy for moving an epidemic around, this is what you do unintentionally. And the great mixing event was long-term market, where there were that many sheep exposed and 180 odd formal purchases. So the infection was beautifully spread. So there was therefore a lot of early dissemination of the infection. A few long-distance movements magnified the problem, and then there was I've never got to the bottom of this really. The first cases were reported on the 20th of February, and the movement orders were initiated on the 23rd of February. The Danes had an epidemic, a smaller one, I think, some years before, and they'd limited movements, because that's where we're trying to keep down the R value, okay, so we're trying to limit the contacts. They brought that in on the same day. My colleague Mark Woolhouse calculated, if this movement ban had been brought in, of course it's very expensive to do, so there's a cost to it. If it had been brought in on the same day, the epidemic would have been maybe half the size. So it would have cost much, much less and caused much less distress. It was a terrible epidemic for the farming community. The other nice thing was then they announced the movements before the movement ban, before they brought it on. And there was an unprecedented peak in movements by the farmers who were not stupid, who moved their animals around when they needed to at a huge rate before the movement ban came in. Okay. So there was therefore huge dissemination of the infection. And the infection here was really much more patchy than measles in cities, as we saw. And it was also an infection of sheep and cattle. And it was really distributed in the west of the country. And a much more disseminated, spatially patchy epidemic, much more irregular. Lots of spikes in it, as you can see. But it's still this discernible epidemic shape with a kind of a long tail. So in terms of understanding what we should do to control it, and a bunch of people were mobilized to think about this, it's a complicated interaction between, there's this epidemic pattern, there's the local spread of the infection, there are a couple of species involved of hosts, sheep and cattle, there's control by movement restrictions and slaughter of farms and culling and so on, and I'll come back to vaccination later. So this means that there's a lot of sums that need to be done to think from a particular standpoint and particular set of assumptions what's going to happen to the epidemic. And therefore, dynamic models, mathematical models, are a useful tool there, and they're no more than that, and they're an imperfect encapsulation of our hypotheses, but they're a useful tool for exploring how these interactions affect the success of control. So the model that we made, and several people made models of various sorts, what you need to know, if you've got an infected farm, how is the infection going to spread? So this is the chance that the infection is going to spread to neighbouring farms, and we can estimate that from the early pattern of the epidemic. And we also knew that there were risk factors. If a farm's got more animals, then it's more infectious. It's got more animals, it's more susceptible to infection. You can quantify those things. And then cows are much more susceptible than sheep to infection. So cows are kind of heaven for the virus here. They acquire the infection considerably more easily. So from the early pattern of the epidemic, and this was really Matt Keeling, could parameterize the model, and this is many runs of the model, so this is a so-called stochastic model. You have to allow for the variability of things against the observed pattern of the epidemic in black. And it was kind of fitted on the early part, so one's got to be cautious in saying how good this is, but it's a reasonable capturing of what we saw. Now what made the epidemic turn over? One of the major things was the pattern of culling, and all the models here, including some models from the ministry, illustrated that the tracing of infection and the local stamping out of infection wasn't sufficient, and therefore more local culling was needed. And this was very controversial and a very terrible thing to do, a heavy responsibility to do, because if farmers have valuable animals, then you need to think, should you really be doing this? But all the models indicated that this was what needed to be done. So why not vaccinate them? But before coming to that, I want to talk about, just briefly, what was learned from this. And this is, if you're interested in looking at lessons learned from epidemics, this is there are a couple of government inquiries. There's one by the Royal Society and one by another group looking at how the government dealt with it, the Anderson inquiry. And here's the list of things you do. Before the epidemic, you stay vigilant, you're prepared, you react with speed and certainty, you explain what's going on, and that wasn't always done. So this is a wish list rather than what they did in many ways. You respect local knowledge, so there will be local expertise. You do proper risk assessments and cost-benefit analyses. You collect the right information. And much of this has to be in place before you get started. You've got the right legislative frameworks to do things. And the science that you do, making the models, making the vaccines, doing the immunology, getting the biology right, has to be the best science. And the scientists really have to explain what they're doing. So this is anyone who's interested in the kind of sociology of this or the planning, then these are interesting sources to look at, I think. For example, in an epidemic in '67, they brought they wrote down that they should bring the army in very quickly to do the logistics, and they didn't do that for a while, quite a long while in the latest epidemic. I think it's written down that they will next time. So as I said, though, next time I'm sure that future control measures would centre around vaccination. There were lots of economic and logistic reasons. I can talk about it later if people are interested why that wasn't done in this case, in the 2001 epidemic. But from our sums earlier on, how much should you need to vaccinate against foot and mouth? So we can use these models to look at this. And again, here's our picture of the critical vaccination proportion against how quickly it spreads. And at the farm level, at the farm-to-farm level, as soon as the movement restrictions have been put in, then you only really needed to, R0 was about 1.5 to 2, you only really need to get about 40% of animals just our simple back of the envelope calculation would say, the one that we did earlier, and applying those complicated models to that. So this is the number of farms you vaccinated, and that's about 40% of them, about 150,000 farms. And this is the size of the epidemic. Then roughly about 40% coverage would achieve stopping the infection spreading. So the complicated model agrees with the simple one here. So it's always good to have interpretations of these things, as in all of science at all scales. And another interesting thing was targeting large cattle farms, which really were also the most valuable animals. Targeting large cattle farms was also particularly useful. So Matt Keeling and his colleagues have been following this up with the government now, with the ministry, and using ring vaccination and smart versions of that to try and control the infection. One of the reasons why that wasn't in place before the last epidemic, and a complication is you couldn't do this prophylactically as you would with measles. You couldn't vaccinate currently because before the epidemic, because there are many strains of foot-and-mouth disease. This is not like measles. For measles, any variability in the virus, you still get the same immunity. But there's zoom back there. Because of that variability, you wouldn't know which strain to give, so you really need to have banks of antigen of the virus, and therefore make the vaccination very quickly when the epidemic comes, or if you know a particular epidemic is going to come. And the vaccinologists are desperately for FMD, and in particular for flu. You know, the holy grail here would be a vaccine that worked against all these sorts of strains for all these infections. But this brings up the idea now that this variability, so the vaccine against one sort of FMD doesn't protect against another, that we need to think about evolution. So this brings me to the second major part of the talk. This strain structure, this evolutionary structure of the virus, brings us to the second question: how does the evolution of pathogens affect this population immunity that I talked about for measles, and therefore our ability to control them? So the classic example here is influenza in humans and other animals. It's an endemic, really, often not dangerous infection in waterfowl, for example, and often spills over and spreads to humans and other mammals. And we know that it causes major pandemics, but it also exerts a considerable toll of infection and death every year, just in between pandemics. So that there's a huge toll from influenza, and part of the reason that there's an epidemic every year is that it keeps evolving, and I'm going to illustrate that just in a minute. So, like measles, influenza is a respiratory virus, so that it's spread by aerosol. It's much less transmissible, so in principle it's much less dangerous. But it's crucially different in that here's the virus, that the surface molecules that get the infection into and out of cells, called hemagglutinin and neuraminidase, they also can be attacked and stuck onto by antibodies, and they're one of the major ways that the virus is combated by natural immunity and indeed by vaccination, just as with measles. But in this case, and it's interesting that measles is the exception here in that works really beautifully. But flu can evolve around that. The virus can evolve to escape previous immunity by changing its surface molecules. So the immune system recognizes them, but it can change through the next time. So what's the process of evolution here? So let's illustrate that schematically. Let's imagine that we've got a viral population here. And the virus here is a particular genotype, it's a particular set of surface molecules, and I'm just going to denote that by colour. But the other thing about these RNA viruses is that they've got tremendously error-prone replication, so that the virus even within an individual, the virus generates tremendous variability. And I'm just denoting this by colour here, so that you generate stuff that's like the parent virus, but there's a lot of variability. Now, all else being equal, and assuming all these viral types work for the moment, let's assume that the prevailing immunity of the epidemic in people is this colour, so that you've got the classic pattern and prerequisites for Darwinian evolution here. You've got variability, and it's heritable variability to some extent, and you've got a selective process. So the selection here would be, and it often is a flu with some complexities, for the biggest colour change, for the biggest difference, the biggest escape from the prevailing immunity, so that this becomes the main virus in the next generation. So this would be one flu season, and then this one would be the next flu season, and another colour would be the next flu season. And therefore, if you got flu in this season or you were vaccinated, then after a season or two, you would need to be vaccinated again. Or if you got the natural infection, then you could get the natural infection again when it had evolved. So that you see, and the evolutionary trees of flu show this, but I'm just showing it schematically here. Through time, there's an escape from previous immunity, a steady escape from previous immunity. This is even in between pandemics. What happens in a pandemic then? Well, you occasionally get new pandemic strains, probably by reassortment, it's called, by recombination of flu strains from different species. For example, birds and humans. So let's say now that we've got our human strain from last time, and the colour inside here is the other genes. So there are other genes that replicate the virus and do various other things. And all that package has to be right for the thing to spread in a given species. So let's say that we've got a very different set of coat proteins now in let's say, bird species, in ducks. But this internal colour, I'm just schematically saying, it's not going to grow in humans. So this won't necessarily at all grow in humans, but it can recombine so that it can, if you got an animal or a human possibly, and it's still not clear exactly how this happens or where it happens, if you get a reassortment, a reproduction between these two, then you can get the surface proteins of the new virus and the internal genes of the other. So that this is then infectious to humans. So this would then be a pandemic event. But it's also got a big immune escape. So that then, in terms of escape from previous immunity, you get a big jump in escape from previous immunity. Suddenly we're at that case in our simple time model where everybody's susceptible. So how does the year-to-year variation, just coming away from pandemics for a second, affect the pattern of population immunity? So again, we've got our little toy model, susceptible, infected, and recovered. And the infected person infects 5 other people, a little bit more uncertain this time, you notice. Infects 5 other people, they infect lots of others, but then these people become susceptible again. So that's the essential step. So now this infected person can infect these people, but they can also infect those others. So therefore there's a jump back from the recovered to the susceptible class. And population immunity is now much less solid than it was for measles. And one science slide here, this is in particular Dr. Shearer, a very technical piece of statistical work here, and something of an achievement, managed to show from, these are time series for flu-like illness from France and from Holland, and you don't see those beautiful patterns of a big epidemic and a little one, and a big epidemic and a little one. You see quite irregular patterns, and what Grenfell was able to do was to extract the strength of immunity that people have as a function of how far it is since they were infected. Now we know for measles that goes on forever, but he was able to show that the strength of immunity is high to start with, but within a season it drops down. So that the only signal here really is that there's this kind of finite immunity. This is an important piece of evidence that goes with the others to show that our epidemic clockwork in flu is very different because of evolution. So just in conclusion then, I've talked about the anatomy of an epidemic and the diversity and importance of parasites. I've talked a bit about spatial dynamics, especially in the context of foot and mouth disease and preparedness and all those lessons. And those websites are interesting if anyone's interested. But the major feature areas are the evolution of pathogens like influenza, HIV, drug and antibiotic resistance, and monitoring and logistics combined with scientific advances in control measures and basic understanding are the key. Thank you very much.
Yep.
Professor Grenfell, please to answer any question. Yeah.
Could you say something about the virtues of different strategies that have been discussed for combating bioterrorism in the United States, where I think the CDC has taken a different position from a number of scientists with regard to the scale of vaccination and so forth?
It's an interesting question. I mean, it depends what. So let me focus on foot and mouth disease, which is also a big threat to the US, because it's one I know more about, and it would be a very easy one. I think it's not a secret to say to introduce. If the infection's introduced in one place, then and let's say it was smallpox, but I think all the models say, and they're based, but they're done by smart people and based pretty solidly on what's happened in the past, that as long as the infection's spotted quickly enough in a timely enough way, if it's only introduced to one place, then, or a few places, the infection can be stopped without mass vaccination. Trade-off with smallpox is, it's currently the vaccine has serious side effects in some people, so there is a cost to vaccinating. If it were measles, you could just vaccinate everybody prophylactically. You're always going to think of the worst case. If you've got it and you're a terrorist, you might introduce it to 100 places. Now, then you might have to mass vaccinate. Also, I mean, I don't know how the politics would work. If there were a serious outbreak and it wasn't being controlled, I think it would be politically essential. It would be political suicide not to mass vaccinate because the clamor would be such that maybe mass vaccination would like to happen. Maybe the public health experts could agree on that. I mean, another interesting thing is linked to that. We have this great herd immunity against measles, and hopefully we can eventually eradicate it from the world. But maybe that in the economic sense, that herd immunity is a pretty precious gift, because if we stop vaccinating against measles now, if we got rid of it, and we waited 50 years, well, it's jumped across from other species before. Most of these infections came from other species. Eventually, it can't be done now, but soon, I guess, people will be able to make measles virus that's infectious. Should we then throw away our herd immunity? I mean, I think those are interesting questions.
Could you say something? I think both the CDC and others tried to predict viral evolution, particularly with regard to influenza from one season to the next, so that they actually can make the appropriate vaccine before the virus appears.
Yeah.
Are they successful in doing this?
It's pretty good, I think, actually, and improving. There are lots of new techniques now for trying to systematize that. They do it by looking at patterns of immunity, so the distance measures between the viruses, to look when there's a jump. I think they're pretty good at spotting what you should do next season. But what they can't do yet is predict the directionality of evolution, right? So they can't say, okay, the season after that, where's it going to be? And if you could know that, maybe you could make a mass vaccination campaign that could stop the virus. So I think from where strains are clustering, because there are two vaccine decisions, northern and southern hemisphere. The vaccines, the strains that are coming up at the end of the season, you can predict, but you can't necessarily predict in a mechanistic way beyond that. But But yeah, I mean, I think they do an incredibly stressful and important job.
Surely the major defence we still have against new diseases, the new disease emerging, when it's first there, is just simply shutting down transportation, shutting down movement. In other words, isolation and quarantine.
Immediate. But the cost of that, I mean, imagine shutting down New York for 3 months. The cost of that. Maybe you've got to do that, but it's absolutely not a trivial decision.
Or at least reducing transportation.
Yeah. And I don't know, one would hope that they're field testing what you could reduce selectively in most terms, because I think that would be in an apocalyptic scenario, that's all that they could have.
Questions according to measles. Apparently it's a great advantage in nature to gain lifelong immunity after having had the infection. Do we know how long immunity lasts after vaccination? And do we have an idea about what problems could emerge from imperfect immunity due to a vaccination which is with a vaccine which is not perfect?
It's last good year, I think they took this group and I looked at that. It's some very nice work in Holland, for example. Yeah, I mean, the artificial immunity isn't quite as good, and it may be wanes eventually. In developed countries, what you do is if those, that wouldn't be apocalyptic, because there's still a lot of immunity there. So you could do booster vaccination. It's a very safe vaccine. You could revaccinate adults. So that's not the absolute worst scenario. I don't think it's going to go like that.
But I want to ask the vaccination for the influenza. Now currently the influenza vaccination, I mean, for example, the WHO global influenza group, they will predict the next predominant strain so that they can produce a vaccine for the next coming epidemic.
Yeah.
So, I mean, but so far still, sometimes WHO still cannot truly predict the next coming epidemic. So, I mean, the particular strain. So, what's the absent part? I mean, the missing information in this projection.
I think surveillance. I think sequencing. I mean, there's another issue that NIH are now doing this a lot. On GenBank every week, I think, doing lots and lots of planning to do lots and lots of whole genome sequencing. I think we need just much more surveillance. And the more there is, and the more mechanistic understanding we get, then the more chance we've really got to. It's a very fragile virus in many ways. It's got a very short infectious period. It could be quite easy to break the chain if you could make a vaccine that works across strains. But there is cellular immunity. People talk about that, but cellular immunity doesn't seem to have stopped pandemics in the past. So whether anybody will make a blanket vaccine, maybe drugs are a better option there. Because then again, I think drug resistance is immunity.
I do have a question. Every 9 months, I go for this flu injection, vaccination. Okay, I suppose that every time it's a different vaccination, right? Because
not necessarily. No, they don't change it. If they don't change it, you should get a vaccination.
but do they know? I mean, why is there a reason for 9 months? And do they know? How is it? Okay. Yeah. Okay. Okay. If there is mutation, all right, there's a mutation of this new virus, like it's 9 months ago, really, the length of time.
I think it's. I'm not looking at it. I think it's annual in the UK and the US. But so I don't know what's in the I mean, another interesting question is that the evolution of the flu is slightly punctuated between, so that it won't change. It's in clusters really. It doesn't change very much for a while, and then there's a jump. So the current vaccine is pretty good for those, but then they're desperate to stop these little jumps that happen. Because then you've had suddenly a lot of people. So then you really want to get, absolutely sure you're vaccinated and they spot one of those jumps.
So probably this 9 months is more to do with how long the immunity means going to last.
Yeah, I think against a particular strain, if flu stopped evolving, it would disappear very quickly. People's immunity will persist for longer against a particular strain. But it's of course evolving.
In the Dutch studies that you did, looking at immunity to influenza, did you look to see how much reduction, how much herd immunity developed before you see a change in the flu, before you spotted the mutations?
No, didn't look at that. The data was too crude for that, really, because we didn't have the flu-like illness subsumes H3N2 years and H1N1B years, so it's across subtypes. And we hoped we could see a pattern of that duration of immunity would change with the clusters within subtypes or change with the jumps across. But no, all we could extract really, and it was despite into extreme efforts last year, was just this signature that there was a short strain transcending immunity. And I think the models indicate you need that to keep the evolution pretty sparse as well. But I think there is evidence that if you've had waves of different subtypes going through, then if there's a short interval between them, then individuals don't get the second one. Whereas if it's many months, then we will. So strain transcending immunity is, I think, really interesting. Whether that's cellular immunity or cytokine immunity, I think it's probably.
In cases where you cannot actually stop movement of things that basically spread the disease, like recent bird flu that is kind of predicted in Western Europe, where birds coming from Russia with SARS. And so in that case, what's the usual strategy?
Well, it depends whether it jumps across, doesn't it? Do you mean that? So there'll be that bird flu, and it's very dangerous to birds. And people who get a very big dose of the flu, I think, as with H5N1, might get infected, and then there's a very high mortality rate. But it doesn't spread human to human. Now, as soon as it spreads human to human, it's at that point that you want to intervene, because if it's pathogenic in birds and it's spreading, but it's not a strain that's infecting humans, well, there's tons of fluid out there that are doing that. So that what you need to do is to monitor. But the key thing is to spot the zoonotic event, spot the jump. And then you want to bring in movement restrictions, huge. At least with flu, we've got the drugs and we can make the vaccines, but it will take a while to make enough of it. So I think it's spotting the zoonotic event, which is obviously what they're obviously desperately trying to do. Spot the jump across, which will, it's happened three times last century, it'll happen again.
Going back to flu, like
suppose you isolate a bunch of viruses from an organism, and suppose you can sequence them.
Yeah.
How much variability do you expect there? And secondly, if there is some variability, how do you find out which are viable and which are just dead ends?
That's a fantastic question. So very little's been done on that. In fact, we're interested in it, and we've been looking at it with equine influenza, which is again flu in horses, because there they do experimental infections, and therefore one can test vaccines, and therefore one can do that. So what you have to do is, and this has been done a bit with HIV, and it's only just begun to be done with flu. So you have to get your viral sample and not culture it in anything, and then clone out the variability. Really, what you'd like to do, since this is a segmented virus, is you'd almost like a sort of nano machine that would have to pick up individual viruses and look at the variability across the whole genome. But let's just think about the surface proteins, so that we find after in day 2 of an infection of one of these horses, compared with the challenge virus that was given initially in naive animals, then there are many amino acid changes. I mean, I think of 50 clones, maybe 30 clones had amino acid changes. So immense variability. That's only after about 6 generations. But second answer to the question, answer to the second part of your question, and this is work with my colleague Amy Holmes, who's a viral phylogeneticist. There are evolutionary trees for those genes in horse flu. So that's what you see at the population level. Many of those variations within hosts you never see in the trees. So most of them are deleterious. So there's this tension you see in the virus between you can produce this variability and you might produce a great, wonderfully different surface protein. But if it's a surface protein that doesn't let you get into cells, then that's no good. So a lot of the variability just gets washed out. The next thing we're trying to do now is transmission experiments to actually see what gets transmitted. But I mean, I think the HIV folks, the classic case is the variability in individuals. In one individual is much bigger than all the consensus flu variability. But I think your question's a brilliant one, because we've got to get beyond the consensus for these sequencing these RNA viruses. We've got to look at the variability within hosts, and I think lots of the people with the money should, and like NIH, really do. I think it's an incredibly important question, because we can't really know what's happening at these bigger scales without knowing how that engine of variability works.
Question? Okay, if not, let's thank Mr. Grenfell again for his